Hey everybody, so from last, I believe, on Thursday's asynchronous, we got a bunch of questions, mostly on 32, 57, and 58. So I'd like to break those down quickly. And so 32 here was telling us to graph the function, then to state the domain and range. So this was in this format where we had explored, which was the ax plus b over cx plus d format. And in this case, we know that the horizontal asymptote, right, what it approaches as x gets infinitely big, positive or negative, is just the ratio of a over c. It's the line, in fact, y equals a over c. So for this function, it would just be negative 2, and since it's a negative x over negative 1, so my horizontal asymptote would be y equals 2, not 1. Y equals 2. That didn't make any sense. Okay, and then the vertical asymptote is basically finding what could x not be. So you could always set this equal to 0 to solve. Subtract 10, divide by negative 1, or multiply by negative 1. So these are my two asymptotes, my vertical and my horizontal. And so this is my first step for wanting to graph, but it also is going to help me answer this question because my domain and range will be all real numbers except the corresponding x or y value. So if I'm to graph this, I could put this here, my axes, and in a different color, let's do red. I have y equals 2 as one asymptote, and x equals 10 as another. Okay, so it'll be, if I go by 2, 4, 6, maybe I should have thought about that sooner, but I'll go by 2s. So this will be y equals 2, 2, 4, 6, 8, 10. This one here. And then what I would do is then plug in a few values for x, see what I get out for y. So if I plug in, for instance, 7, I would get out negative 11 thirds. If I plug in 8, I would get out negative 13 halves. If I plug in 9, I would get negative 15. If I now plot some to the right of the asymptote, if I plug in 11, I got out 19, 12, 21 halves, and then 13, 23 thirds. I had done this separately, so that's why I'm able to do that so quickly. But now that I have those points, so this would be 8, 7, negative 11 thirds. 8, negative 13 halves, actually this one will be more like here, just to be nitpicky. And then 9, negative 15, 2, 11, 19 would be way up top. I don't know, it's just a ballpark. 12, 21 halves, so that's a little bit, 10 and a half. And then 13 would be 23 thirds, which is a little bit more than 7. 7 and 2 thirds. So I could then draw my graph. It's not perfect, but I run into my axes. So the last part of the question is to say what would be the domain and the range. So the domain is the x values. It's all real numbers except for 10, which is, right, it's approaching 10, but it's never going to reach it, but it's going to have all the other numbers. And then the range would be all real numbers except the y value of the asymptote, right? It's all y values except for 2. So that's number 32 there. 57 was another one there were some questions about. And 57 was giving us 2 internet service provider plans. They tell you you have one that's $50 installation and monthly fee of $49. And the table shows the average monthly cost of Y of a competing provider to the one they described there. So be 50 installation plus 43 per month divided by a number of months would give you this. So that's why it's a rational function. Well, if the cost of the second plan would be 50 plus 43 over x, if x is the month, I guess I could say divided by the number of months, right? This would tell you the total cost divided by the number of months. So to me, going to my calculator would be a wise strategy here. Watch, I put in my equation here, and I've set my table actually so that it starts at 6 and changes by 6, because that's the way the other table was presented. And look, I can compare. Well, at 6 months it's 51 1/3, so it's more expensive. At 12 months it's $47, which is still more expensive. At 18 months though, it's $45.78. So somewhere between 12 and 18 months you would want to choose the original plan. This competitor's plan we see is cheaper at 6 and 12 months, whereas it's more pricey start at 18 and 24 months. So we would say we would choose the competitor as the better choice for x equals 6 and x equals 12, but more expensive at x equals 18 and x equals 24. Okay, and then the last one here was 58, and this one was talking about the Doppler effect. So if you hear an ambulance coming towards you, you may notice it's higher pitch, and then when it's driving away, lower pitch, because of the way that the sound waves are moving more rapidly when the ambulance is driving towards you. So it's telling us that it's a source of sound moving relative to a listener. Frequency is heard by the listener is different than the frequency at the source. So in both equations below, we have to incorporate something where r is the speed of the sound source. So if it's moving away from you, we're dividing by 740 plus r. If it's approaching the listener, it will be minus r. And so what you could imagine is that if we're dividing by a plus r, it's going to make the frequency lower, so it's going to sound lower, where when it's moving towards you, the frequency is higher because we're dividing by a smaller number. So they're telling us that if a siren has a frequency of 2000 hertz, so the f of s is the frequency at the source, so that doesn't, and write two equations modeling the frequencies heard when the ambulance is approaching and when it's going away from you. So, well, I'm basically plugging in here, so it'd be 740 times 2000 over 740 plus r. They don't tell us the speed, so this would be away. The frequency of the listener would be this, and this would be towards or approaching the frequency of the listener would be the exact same thing except minus. So nothing too fancy there, but let's see how it plays out. And so let's graph these two equations. So if I were to graph these two, what I would see is that my asymptote is going to be different. So if I were to graph these by hand, I could see that my asymptote would, for this one, be negative 740, and this one would be positive 740. Graph, I'll pull it over here from 0 to 60. You'll see that they almost look like lines, but this top one being when it's approaching, because the speed of it coming towards you is increasing the frequency where it's going away. But look, if I zoom out, these are actually two reflected hyperbolas. But when we zoom in at this part, you can see they look almost linear in that piece, although we know that there is some curvature given that they're a piece of a bigger one. So the final part of the question is then, for any speed r, how does the frequency heard for an approaching sound source compare with the frequency heard from the source moving away? Well, the simple answer to that question is that the frequency that you hear is greater when it's approaching, right? Whereas the frequency you hear when it's going away from you is lower. And those are both modeled by these two graphs. So next time you're out listening to a siren, if you happens to drive right by you, it'll go wah, 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 wah. You probably heard that before. That's called the Doppler effect, and it's modeled with a rational function that's actually hyperbolic. Wow, whoever was finding all these things is quite amazing, huh? Have a great day, everybody.